chapter 6 of concept of mole and chemical counting, chemistry, English version. So we have finished up to this math, and now what we are going to do is we are going to keep solving these mathematical problems. Okay, we're going to skip a few, give you homeworks because we don't have much time, right? So what is the molarity of the solution when there is 20 gram Na2CO3 in 250 ml solution? So what do we have? Let's write that down. We have 20 grams of Na2CO3 as we have counted in our previous class. The molar mass of Na2CO3 was what? 106 gram. The molar mass of Na2CO3 was 106 grams. Okay, molar mass. Molar mass. Mass of 1 mole of Na2CO3 molecules. So now we have 20 gram of Na2CO3. So let us calculate how much mole of Na2CO3 we have. So if mass of 1 mole, if mass of 1 mole of Na2CO3, if mass of 1 mole of Na2CO3 is equals to 106 gram, I can reverse that. I can write down as such. That means 106 gram is the mass of 1 mole of Na2CO3, right? Therefore, 1 gram is the mass of 1 by 106 mole of Na2CO3, right? Or 20 grams is the mass of 20 divided by 106 moles of Na2CO3. So how much is that? Let's calculate. 20 divided by 106. 20 divided by 106. 0.1886. 0.1886 moles of Na2CO3. 0.1886. So we have 0.1886 moles of Na2CO3. Now what is our question? What is the molarity of the solution when there is 20 gram or 0.1886 moles of Na2CO3 in 250 ml solution? So 0.1886, remember that 0.1886 moles of Na2CO3 we have, okay? And we have 250 ml solution, 250 ml solution. Now once again, I'm going to remind you 250 milliliter is equivalent to 0.25 liter. How? In order to understand this, you have to watch my previous class, okay? So now we have in 0.25 liter solution, we have 0.1886 moles of Na2CO3. Therefore, in 1 liter solution, we have 0.1886 divided by 0.25 moles of Na2CO3. And remember, whatever moles of any substance or any solute that we have in a 1 liter solution is the molarity of that substance. So let us calculate. 0.1886 divided by 0.25, that is 0.754. 0.754. Our molarity is 0.754, and we always represent molarity with a capital M. Okay? Good. Did you understand? If you did not, please let us know in the comment below. We're going to be fast because we have to finish all the mathematical problems. What is the volume of the solution in milliliter when 20 gram Na2CO3 is dissolved in 0.75 molar Na2CO3 solution? Once again, since it's 0.75 molar or 0.75 capital M represents molar solution. That means in 1 liter solution, 0.75 moles of Na2CO3 is dissolved. Am I right? Does that make sense to you? 0.75 molar solution or 0.75 capital M means in 1 liter solution, in 1 liter Na2CO3 solution, dissolved solution, aqueous solution, 0.75 moles of Na2CO3 is dissolved, right? Therefore, now, okay, so now we have 20 grams of Na2CO3. So 20 grams of Na2CO3 was how much mole of Na2CO3? From the previous math, we can understand that there was 0.1886 moles of Na2CO3 from the previous math, right? So we can use this in a unitary method, and we can say that if 0.75 moles of Na2CO3 is dissolved in 1 liter solution, therefore 1 moles of Na2CO3 is dissolved in 1 by 0.75 liter solution, and therefore 0.1886 moles of Na2CO3 is dissolved in 0.1886 divided by 0.75 liter solution. Now how much is that? How much is that? 0.1886, 0.1886 divided by 0.75, that is 0.25, okay, 0.25. Now 0.25 is in liter, right? 0.25 will be calculated in liter. So if I want to convert liter to milliliter, I will multiply it with what? 1000. So 0.25, I'm sorry, 0.25 into 1000, that is 250 milliliter. That is my required answer, okay? That is my required answer. Okay, this is the same problem. You can do it yourself. I'm not going to repeat it. The same problem. You are to find the molecular mass of Na2CO3 through the different variation of unitary method. The answer is going to be 106 grams. Okay. How do you prepare? How will you prepare? How will you prepare 200 ml semimolar? Now, I told you semimolar means in 1 liter solution. Semimolar means in 1 liter solution, there is 0.5 mole of solute dissolved. Okay, solute dissolved. In 1 liter solution, 0.5 moles of solute is dissolved. In 1 liter solution, 0.5 moles of solute is dissolved. Okay, semimolar. Now, I do not have 1 liter. I have how much? 200 milliliter. 200 milliliter means 200 divided by 1000, that is 0.2 liters. Okay, 0.2 liters. So therefore, in 0.2 liter solution, 0.5 into 0.2 moles of Na2CO3 is dissolved, since the solute is Na2CO3. So how much Na2CO3 is that? 0.5 into 0.2. 0.5 into 0.2 is what? 0.1. Okay. 0.5 into 0.2 is 0.1. Okay. 0.1 moles of Na2CO3. So I have 0.1 mole of Na2CO3. What is my question? How will I prepare? So how much do I need? I will need to convert this 0.1 mole of Na2CO3 into grams. That is my required answer. My answer will always come in grams, that this much grams of Na2CO3 is required to create a semimolar solution in 200 ml. Okay. So I have 0.1 moles of Na2CO3. Remember this, okay? I have 0.1 mole. Now, I know mass of 1 mole of Na2CO3 is what? 106 grams. Therefore, mass of 0.1 mole of Na2CO3 is 106 into 0.1 grams or 10.6 grams. This is my required answer. Okay. You can take 10.6 grams of Na2CO3 in a 200 milliliter pot, and then you can create a semimolar solution of Na2CO3. Okay. So I'm going to do only one of this, and the other is going to be homework for you. Okay. Okay, find out the molarity of the solution when there is 4 gram NaOH in a 100 ml solution. Now, what is given? The volume is given 100 milliliter, or this is equivalent to say 0.1 liter. If you do not know how to convert, I have discussed this in my previous video. You can follow the previous video. Now, I have 0.1 liter solution and I have 4 grams of NaOH. I have 4 grams of NaOH. Now, what is the molar mass or the mass of 1 moles of NaOH molecules? What is the mass of 1 mole of NaOH molecules? Well, from the periodic table, the mass of sodium is 23, the mass of oxygen is 16, and the mass of hydrogen is 1. How much is that? 40, okay? 40 grams. 40 grams is the molecular mass or the mass of 1 moles of NaOH molecules, okay? Is that understandable? Let me repeat it once again. The mass of 1 mole of NaOH molecules is 40 gram. Okay? Okay. So if 40 grams is the mass of 1 mole of NaOH molecules, therefore 1 gram is the mass of 1 by 40 moles of NaOH molecules. Therefore 4 grams is the mass of 4 by 40 moles of NaOH molecules. Is that understandable? What is 4 by 40? 1 by 10, 0.1, right? So we're going to do 4 by 40. that is 0.1. Okay. So I actually have 0.1, I actually have 0.1 mole of NaOH molecules, okay. Okay, so I'm going to erase this. I'm going to erase this. So let me repeat. I have 0.1 liter of solution and I have 0.1 mole of NaOH molecules. I have 0.1 mole of NaOH molecules. Now, my question is, what is the molarity? And the molarity is always calculated in 1 liter, okay. The amount of mole, okay, the mole of that solute in 1 liter solution is my desired molarity, okay. So now we can use the unitary method once again, all right. So in 0.1 liter solution, I have 0.1 mole of NaOH molecules. In 0.1 liter solution, I have 0.1 mole of NaOH molecules. Therefore, in 1 liter solution, I will have 0.1 or 0.1 divided by 0.1, that is 1 mole of NaOH molecules. So my molarity is 1, okay. My molarity is 1. What is molarity? The molarity is the amount of moles in 1 liter solution of that solute, okay. Okay, this is going to be a homework for you, this one. So today we are going to calculate the percentage composition of elements in compounds. Now you have the formula right here. The percentage composition of element in a compound is the atomic mass of that element that you get from where? The periodic table, okay. So what is the atomic mass? The atomic mass here that we are going to use is actually the mass of 1 mole of that atom that we derive from the periodic table. Into the number of atoms, you can see this below that number, let's say H2SO4. Let's say H2SO4. So how many hydrogen atoms are here? 2, okay, because there's 2 here. How many oxygen atoms are here? 4. How many sulfur atoms are here? 1. Atomic mass of element, number of atoms into 100 divided by molecular mass, the total molecular mass of that compound, okay. So let us calculate H2SO4. In your book, HCl is given, so I'm not going to do it again. What I'm going to do is, I'm going to solve H2SO4, okay. So I'll do this slow because this is the first time you're doing it. H2SO4, calculate the percentage composition of elements. How many elements how many elements are the constituent in H2SO4? There is hydrogen, there is sulfur element, there is oxygen element, okay. How many elements make up H2SO4? There is the hydrogen element, there is the sulfur element, and there is the oxygen element, okay. So now from the periodic table, 1 gram is the mass of 1 mole of hydrogen atoms. 1 gram is the mass of 1 mole of hydrogen atoms. Sulfur is 32, right? We know sulfur is 32. 32 grams is the mass of 1 mole of sulfur atoms. 32 gram is the mass of 1 mole of sulfur atoms, and 16 grams is the mass of 1 mole of oxygen atoms, okay. Now, if we use these values to calculate the molecular mass of H2SO4, I will get the mass of 1 mole of H2SO4 molecules. Does that make sense to you? Because this 1 gram, this 32 gram, 16 gram, these are what? This is the mass of 1 mole of these atoms of these elements, okay. So if these are the mass of 1 moles of hydrogen, sulfur and oxygen, so when I use these values to calculate the molar mass of H2SO4, I actually get the mass of 1 mole of H2SO4 molecules. So that will give me, I have 2 H atoms right here, so 1 into 2. Why 1 into 2? Because 1 gram is for 1 hydrogen atom, 1 mole of hydrogen atoms, 2 meaning 2 moles of hydrogen atoms, therefore 2 into 1, okay. Sulfur, there is only 1 sulfur, so only 132 plus oxygen, there are 4 oxygen atoms, therefore 16 into 4. How much should that give me? That should give me 98 grams. You can do it for yourself. However, I'll do it for you. This should give you 98 grams. The total molecular mass will be 98 grams if we use the individual values derived from the periodic table, okay, 98 grams. 98 grams is the molecular mass of H2SO4. Okay, I'm going to erase this. Okay, you can take a screenshot if you want to. Now I'm going to erase this. So I'm going to write the formula for percentage composition. What is the percentage composition of element in a compound? So what is the compound here? The compound here is H2SO4 or sulfuric acid. So I'm going to calculate the percentage composition of each and every element that constitutes this compound, like for hydrogen, for sulfur, and for oxygen. Okay. So percentage composition of an element, percentage composition of an element, percentage composition of an element in a compound is equals to atomic mass of that element, that we derive from the periodic table. This is for your understanding. Atomic mass of that element derived from where? The periodic table, into number of atoms that you will find at the subscript, okay, that you will find at the subscript, number of atoms into number of atoms, okay, divided by the molecular mass, or the mass of 1 moles of that molecule that we have just calculated. For H2SO4, this was 98 grams, okay, and the whole thing must be multiplied with what? 100 for percentage, okay. So for hydrogen, this is my molecular formula of H2SO4, right? So for hydrogen, what is the mass of 1 mole of hydrogen atoms that we derive from the periodic table? It's 1 gram, right? It's 1 grams. Into how many hydrogen atoms are there in the compound? 2. Divided by what is the total molecular mass? 98. And the whole thing must be multiplied with what? 100. So what is my answer? 2 divided by 98 into 100. You can do it yourself. 2 divided by 98 into 100. That is 2.04%, okay? 2.04%. 2.04%. 2.04%. This is the percentage composition of who? Hydrogen. Percentage composition of who? Hydrogen. This is for hydrogen, okay? Now we are going to do the same for sulfur. Should I erase this? So I'm going to keep the formula. Now we are going to do it for sulfur. Okay? Okay. Now for sulfur, what is the mass of 1 moles of sulfur atoms that we derive from the what periodic table? We derive it as 32. And how many atoms of sulfur are there? 1 into 1 divided by what is the total molecular mass of the compound? 98. So that gives me 32 divided by 98, and the total thing must be divided by what? 100. Okay, let's do that. 32 divided by 98, and the total thing multiplied with 100. 32.653%. 32.653%. 32.653%. This is the required percentage composition of sulfur. Okay. All right. Now do the same for oxygen. We'll do the same for oxygen. Okay, we'll do the same for oxygen. Now I know that the mass of 1 mole of oxygen atoms that I derive from the periodic table is 16. Okay. From the periodic table, the mass of 1 moles of oxygen atom is 16. And I have 4 oxygen atoms in this compound. Therefore, 16 into 4 divided by 98. Let's do that. Okay, that's going to give us what? 65.3%. Okay, 65.3%. That will give us 65.3%. Okay, that's how you calculate the percentage composition. Okay, you can try this for yourself. Okay, They have used the unitary method here. I have always found this contradictory to how I understand it. I understand this better with the formula and the mole maths with what? Unitary method, but they have done just the reverse. But that's fine. Why have they subtracted that amount from 100? Because remember, in any compound, the percentage composition of individual elements will always add up to 100. Okay. So if the percentage composition of hydrogen is 2.74, chlorine must be 100 minus 2.74. That's a shortcut. Okay. Okay, so once again find out the percent composition of hydrogen and oxygen in H2O. It's very easy. It's very easy. I know the atomic mass of hydrogen is 1 gram. Where did I derive that from? The periodic table. I know the atomic mass of oxygen is 16 grams. Where did I derive that from? From the periodic table. Once again, these are the mass of 1 mole of hydrogen atoms and 1 mole of oxygen atoms. Okay. And what is the molecular mass of H2O that I can calculate using the values derived from the periodic table? It is 18 gram. Okay. 16 plus 2 into 1. 16 is for this, 16 into 1 because 1 atoms, 2 into 1 because each of them weighs 1 gram, okay, 2 because there are 2 atoms, okay, that is 18 gram. So now if you follow the formula, percentage composition for hydrogen in H2O will be what? 1 into H2O. There are 2 hydrogen atoms, right? Divided by 18 into 100. 2 by 18 into 100. How much should that give me? How much should that give me? .11, okay? 11.11%, 11.11%, okay? 11.11%. Now, as I told you, the percentage compositions of each individual elements in a compound should always add up to what? 100, okay? So, I know that water is composed of hydrogen and oxygen. Water is composed of hydrogen and oxygen. Now, if the percentage composition of hydrogen is 11.11, sorry, I'm so sorry, that's not how you say it, 11.11. If the percentage composition of hydrogen in water is 11.11, percentage composition for oxygen in the same compound or in H2O must be 100 minus 11.11 or 88.89%. Okay. Oh, they have done this math actually, and they have the similar values like us. Okay. So, what happens when there is a bracket? What happens? What is the percentage composition of each individual elements in aluminum sulfate? What happens? So, this is composed of 3 elements. This compound is composed of 3 elements. There is aluminum, there is sulfur, and there is oxygen. Okay? Aluminum, sulfur, and oxygen. Now, we will follow the same formula, we will follow the same pattern. The only difference is we need to calculate the number of atoms in the compound. So, what is the number of atoms in this compound? What is the number of aluminum atoms? 2 aluminum atoms. How many atoms of sulfur is there? 3. Okay? Whenever we calculate S, the number of atoms for S, we will calculate using 3. Why? Because this 3 is distributed with sulfur as well as oxygen. Okay? As well as oxygen. And for oxygen, this 4 must be multiplied with 3. Okay, 3 4s are 12. That will be 12. Let me do this for you. Okay, let me do this for you. So for aluminium, what is the mass that I derive from the periodic table? That is 27. Okay, and how many atoms are there? 2. So 27 into 2. Divided by what is the total molecular mass? The total molecular mass is 342. 342 into 100%. For sulfur, I know the mass from the periodic table is 32. 32 into how many atoms are there of sulfur? Since the 3 belongs to the whole bracket, I'm going to use 3 for sulfur and 3 into 4 for oxygen. So for sulfur, it's going to be 3. And for oxygen, the value will be 16. 16 is the mass that I derived from the periodic table for oxygen. And there is already a 4 right here and 3 outside the bracket. So 4 into 3, 12 divided by 342 into 100%. You can calculate for those answers. This is going to be your task, home task. Okay. So today we are going to discuss empirical formula. We are going to discuss empirical formula and molecular formula. Sorry. What is empirical formula? Empirical formula is the simple whole number ratio, at which the elements combine with each other in order to form a compound. Okay, the simple whole number ratio, and at this ratio, elements will combine with each other in order to form a compound. Okay, simple whole number ratio. This is a simple whole number ratio that we will always approximate. Let's say we have 2.12, okay, and 3.98. We can approximate to 2 and 4. We will always approximate this empirical formula to a whole number, simple whole number ratio. This must be a whole number ratio, okay. The simple whole number ratio at which the atoms will, the elements or the atoms of that elements will combine with each other in order to form a compound, okay. How can we find that? Okay, you have the steps in your book. Step 1, the percent composition of the elements is to be divided by their atomic mass. So remember, in your question for empirical formula, the percent composition will always be given, okay. The percent composition will always be given. So we have, let's actually solve this problem step by step, okay. Suppose in a compound, so what happens is, suppose in a compound, let's say a compound X is a compound. Suppose in a compound X, the percent composition of carbon is 92.31%, okay, and the percent composition of hydrogen is 7.69%, okay. This is your question. You're given the what? The percentage composition of the individual elements in a compound. Let's call the compound X, and the percentage composition that you are given with in the question is that carbons is of 92.31 and hydrogens is of 7.69%, okay. Now you have to find out the empirical formula. Now step 1. Step 1 would be dividing the percentage composition, without the percentage sign. We know that the percentage sign represents what? 1 by 100. Please do not use the 100, do not use the 1 by 100 in the value, only the value of the percentage, okay, only the value of the percentage, not the sign. The sign represents what? 1 by 100. So we are not going to use the sign, only the value. Okay, so we are going to divide that value. For carbon, we are going to divide the percentage composition value, magnitude of the percentage composition. We are going to divide it by what? The atomic mass of carbon. And we know the atomic mass of carbon is 12. Where did we get that from? Where did we derive that from? The periodic table. Once again, the periodic table. You need to keep a periodic table in front of you at all times whenever you're studying chemistry. Okay, and that should give us, let's do it, let's calculate it. That should give us 7.692, okay, 7.692. 7.692. Similarly, for hydrogen, this value will be 7.69 divided by 1. Once again, where did we get that 1 from? From the periodic table. This 1 is the mass of 1 moles of hydrogen atoms, okay. 7.69, 7.69. This is step 1. Step 1 is, once again, I'm going to repeat it. Step 1 is dividing the percentage, only the magnitude of the percentage composition by the atomic mass of those individual elements. Okay. Okay. Step 2 would be comparing them with the help of a ratio. Now, what is the carbon is to hydrogen ratio that we have just obtained in step 1? It is 7.692 is to 7.69. Once again, you need to remember it this way. That's not the whole concept of it. Why we do this is sort of a back calculation to understand the simplest ratio at which carbon and hydrogen should bind. Okay, so we are going to make a ratio. We are going to make a ratio at step 2. And we are going to try to convert this ratio into whole numbers. Now, as I told you, we will always approximate. Okay, into a whole number. So, can we say this 7.69 and 7.69 are pretty much similar? I can easily ignore the 2. Why? For the ease of calculation. For the ease of calculation, see, when they become similar, I can divide them both by the same number. I can divide them both by the same number, I'm sorry. And I will have a perfect ratio of 1:1. Or I could actually keep the 2. This would have been 1.0000 something. I could ignore that 0.00 something. I'm always going to approximate, okay? I'm always going to approximate. It's fine. You can approximate here, okay? So, my ratio is 1:1. Now, what does this ratio mean? This ratio means that in step 3, I'm going to erase this, okay? In step 3, this ratio means in step 3, I will take 1 carbon and 1 hydrogen. Why? Because they bind at the ratio of 1:1. So, 1 carbon and 1 hydrogen, I will keep them together, and this will be my required empirical formula. This will be my required empirical formula. Remember, empirical formula does not necessarily have to be the same formula as the individual molecular formula. This is the basic binding ratio. Okay, this is the basic binding ratio. Carbon and hydrogen always bind at this basic ratio, and then you can multiply them. You can increase the number of atoms at the same multiple as carbon and hydrogen. Let's say if you multiply this with 2, C2H2, or by 3, C3H3, but the ratio will always be the same. Okay, the ratio will always be the same, but you can multiply them to get your desired molecules. Okay, but this empirical formula represents the simplest ratio at which carbon and hydrogen will bind. Okay. So, CH is my empirical formula, C1H1 or CH is my empirical formula. Okay. So, I actually have a math for you. We will solve this together. So, in a certain compound X, the percentage composition of carbon is 52.14%, 52.14%, okay? And the percentage composition, okay, for carbon this is 52.14%. For hydrogen it is 13.13%, okay? And the percentage composition for oxygen is 34.73%, okay? Is that understandable? Now, what is the empirical formula? Number 1 question is, what is the empirical formula? And number 2 question is, what is the molecular formula if the mass of the molecule, what is the molecular formula if the the mass of the molecule, or the molecular mass, actually let's write molecular mass, if the molecular mass of a certain variation of the X compound is 138.204, sorry, not certain variation of the X compound. If the molecular mass of X compound is 138.204 grams. Okay, so what is given? The percentage composition of each element that makes up the compound X is given. And number 1 question is, what is the empirical formula? And number 2 question is, what is the molecular formula if the molecular mass of the X compound is 138.204 gram. 138.204 grams. Okay, this is grams, this is G. Please write down the question or take a screenshot. Okay, I'm going to erase this. Okay, so what is the first step? Remember, what was the first step? The first step was you have to divide the percentage composition, the magnitude of percentage composition by the atomic mass of that element. So 52.14, once again we are not going to use the percentage sign because the percentage sign represents 1 by 100. We are not going to use that, only the magnitude, okay, divided by 12. How much does that give you? Let's calculate. How much does that give me? 52.14 divided by 12. 4.345. 4.345. Okay, for I believe hydrogen, yes. I believe for hydrogen, the percentage composition was 13.13 divided by, once again from the periodic table, I obtain the mass of 1 moles of hydrogen atoms as 1. So I'm going to use that as an atomic mass and I will get 13.13. Okay, something divided by 1 is the same number. And for oxygen, 34.73 divided by 16, once again the 16 is derived from the periodic table. This will give me 34.73 divided by 16. This will give me 2.17. 2.17. Okay, 2.17. So these are the value obtained from step 1. We will keep them and we will erase the rest. Okay, we are going to proceed to step 2. What was step 2? Making a ratio of these 3 elements. Okay, making a ratio of these 3 elements. That was step 2. Okay. So the previous one was easy, right? The previous one was easy. But this one's tough because the numbers are not at all in line. They do not seem like a whole multiple of each other, right? Now what can we do? 2.17, what can we do? What's the 2.17 approach? 2.17. What we're going to do is, actually let me use a different color. Let me use a different color. What I'm going to do is, I'm gonna use the smallest value out of these 3. 4.345, 13.13, 2.17. The smallest value is 2.17. At such cases, when you don't know what to multiply it with, what we do is we are going to divide each of the numbers in a ratio by the smallest number, that is 2.17. Why should we do that? Because we can approximate, as I've told you. Okay, you can always approximate. So let's see if we find something similar, and if we approximate it, we might even find a whole number, right? We always do that. And in a ratio, remember, we can always multiply each of the term of the ratio with the same number. We can always divide each of the term of the ratio with the same number. Okay, we can multiply or divide each of the term of a ratio in a ratio by the same number, which is why we are going to divide each of them. We are going to divide each one of them by the smallest number, that is 2.17. So this will be 1, this will be 1, What's this going to be? 4.345 divided by 2.17. 2.17. 2.002. 2.002. And this is going to be 13.13 divided by 2.17. 6.05. Okay. Please tell me you have the same number, or else there is something wrong with your calculation. So this is the ratio that I have obtained. As I told you, you can always approximate in order to bring a whole number. So 2.002, a 0 after a point, you can easily approximate it to what? A whole 2, okay? A whole number, that is 2. 6.05 similarly can be approximated to what? 6. So the ratio becomes 2:6:1, and 1 is just 1. 2:6:1. C is to H is to O is actually equals to 2:6:1. This means the ratio, or the empirical the ratio at which CH and O will bind in this compound will be C2H6 and O1, okay? Or the 1 can be ignored, not ignored actually, I don't have to write that down. Nothing means 1. No number will automatically mean 1. And this is my required empirical formula. This is my required empirical formula. This is my required empirical formula. This is the answer to question number 1. Okay, this is the answer to question number 1. This is the answer to question number 1. Okay, I'm going to erase the whole thing. So this is my empirical formula, okay? So now my next question was, if the molecular mass of X, if the molecular mass of X was 138.204 grams, what is the molecular formula? As I've told you, in order to find the molecular formula, we can multiply each of this number of atoms with the same number, but we have to do it exactly at this ratio, okay? So can we say that I'm sorry. So can we say that the molecular formula will be a whole number multiple, and n is any number, n is any whole number, okay? A whole number multiple of this exact empirical formula where I multiply each of this number of atoms with n, and I will find my desired compound X, okay? Desired compound X. Now, what is the mass of one carbon atom? Not necessarily one carbon atom. What is the mass? Since I derive it from periodic table, what is the mass of 1 moles of carbon atoms? What is the mass of 1 moles of carbon atoms? That is 12. And how many carbon atoms do we have here? 2. So this is the mass of 2 moles of carbon atoms, plus similarly 1 into 6. For hydrogen it's 1, for oxygen it's 16, and the whole thing can be multiplied with what? N. Why? Because n represents that one single whole number that I am going to multiply with the number of atoms in order to get my desired compound X. So according to question, since this is all in terms of mass, this should be equal to 138.204 grams. This is in grams, n is a whole number, therefore this is in grams as well. The units are should be equal on both sides, okay? So let's calculate the value of n. Let's calculate the value of n. (46n) 46 into n is equals to 138.204. Therefore, n is equals to 138.204 divided by 46. 138.204 divided by what? 46. that is going to give me 3.004. Once again, n is that whole number, that we are going to multiply with all of this, each of this number of atoms. Therefore, it must be a whole number, right? So this can be approximated to 3. This can be approximated to 3. Why? Because there is a 0 after a decimal. So this can be approximated to 3. Therefore, n is 3. Therefore, my desired molecular formula, what was my desired molecular formula? My desired molecular formula was this. Okay. So what is my desired molecular formula? It is C2H6O into 3. Okay, into 3. That is C2 into 3 what? 3 2s are 6, C6, H 6 into 3 is how much? 18, and O into 3, O3. This is my desired molecular formula. I have multiplied each of these number of atoms with 3 because 3 was the value that I got of n. Therefore, 3 2s are 6, 3 6 are 18, and O 3 into 1, 3. This is my desired molecular formula, and that answers my second question. Okay, so I have the answer to both the questions, my empirical formula and my molecular formula. So whenever you're given the molecular mass of a compound, this is exactly you can find the value of n. Okay, the whole number, convert it into a whole number, approximate it, always approximate these numbers in order to create a perfect ratio, and then in order to obtain a perfect number of n, perfect value of n, and then multiply each number of the atoms with this n, and then you'll get your desired molecular formula. So this is going to be a homework for you. This too is going to be a homework for you. Okay, this and this are going to be homeworks for you, and in the next class, we will discuss chemical reactions, chemical equations. We have actually done all of it. Okay, they have identified the molecular formula from the empirical formula. We've already done that. So we will discuss in the next class the chemical reactions and chemical equations. That's it for today. Thank you so much for bearing with me. Okay.